There is a natural oil that costs $3 at any hardware or grocery store, lubricates mechanical components more effectively than standard petroleum products under high temperature and high load conditions, and was the preferred lubricant of every major industrial facility in the Victorian era, documented in engineering manuals from the 1800s as the standard maintenance oil for the machinery that powered the first industrial revolution. A lubricant that kept the textile mills of Lancashire running, that maintained the precision instruments of Victorian engineering workshops, and that every trained mechanic of the period applied to moving metal parts as automatic and unquestioned practice. The $60 billion synthetic lubricants industry replaced it after the postwar industrial expansion with petroleum-derived compounds that required regular scheduled replacement, generated recurring service revenue, and could be protected behind proprietary formulations that a natural agricultural oil could never support. Linseed oil, pressed. From the seeds of the flax plant, the same plant that has clothed human beings since ancient Egypt, was not replaced because it failed. It was replaced because it worked too well for too long at a price point that made recurring revenue impossible to sustain. Welcome to this channel. Subscribe and hit the bell. This is where we share what the maintenance industry left behind. Let me take you back to where this all begins. The year is 1840 in the textile manufacturing region of northern England, and a mill maintenance engineer is walking the floor of a spinning facility checking the condition of mechanical components that must run continuously to keep the facility productive. His maintenance kit contains raw linseed oil, a collection of brushes and cloths, and the accumulated practical knowledge of an engineering tradition that had been refining its understanding of metal-on-metal lubrication since the first water-powered mills began operating in the 17th century. Every bearing surface, every gear mesh, every sliding mechanical interface in that facility receives a periodic application of linseed oil as standard maintenance practice. Not because linseed oil was the only available option, but because generations of practical engineering experience had confirmed it produced reliable lubrication performance across the temperature and load conditions of industrial machinery with a film persistence that competing natural oils could not consistently match. John Musprat's Chemistry, Theoretical, Practical, and Analytical, published in 1860, and one of the most comprehensive technical references of the Victorian era, devotes detailed sections to linseed oil's lubricating properties and documents its application in precision instrument maintenance, textile machinery, and agricultural equipment with the confidence of a reference work recording established industrial practice. Here's exactly why it works. And this is the part that makes the synthetic lubricant industry uncomfortable to address in any direct technical comparison with natural alternatives. Linseed oil is composed primarily of triglycerides with an unusually high proportion of alpha-lanolenic acid, a polyunsaturated fatty acid that gives linseed oil its distinctive drying and film-forming properties. When linseed oil contacts a metal surface, it undergoes a gradual oxidative polymerization process, the same process that makes linseed oil the basis of oil paint, that bonds a thin, flexible film to the metal surface at the molecular level. This film does not simply sit on the metal surface waiting to be squeezed out under load. It chemically bonds to the surface and maintains lubrication even under conditions that displace conventional petroleum oils from the contact zone between moving surfaces. The polar nature of linseed oil's fatty acid molecules creates a natural affinity for metal surfaces through a mechanism called boundary lubrication, the fatty acid. Molecules align perpendicular to the metal surface and form a structured molecular layer that resists displacement under load more effectively than the non-polar hydrocarbon molecules of conventional petroleum lubricants. A study published in Tribology International in 2011 tested boundary lubrication performance of linseed oil against conventional mineral oil and a leading synthetic lubricant across standardized load conditions. Here is where the story gets interesting. The global lubricants market generates over $60 billion annually with synthetic and petroleum-derived products, commanding the dominant share of industrial and consumer maintenance spending. The transition from natural oil lubricants to petroleum-derived alternatives following the post-war industrial expansion was driven by the commercial development of the petroleum refining industry and the availability of petroleum-derived lubricating oils in quantities and at prices that made natural alternatives commercially uncompetitive in bulk industrial purchasing. Synthetic lubricant development accelerated through the 1950s and 1960s as petroleum companies invested in formulations that could be protected behind proprietary additive packages, specific combinations of anti-wear additives, viscosity modifiers, and oxidation inhibitors that could be patented, trademarked, and marketed as technically superior to both natural alternatives and competitor formulations. The commercial logic was straightforward. A lubricant requiring scheduled replacement every few thousand miles or every few months of operation generates predictable recurring revenue. A natural oil that bonds to metal surfaces through oxidative polymerization and maintains film integrity for extended periods generates far less recurring revenue. Linseed oil cannot be patented. The knowledge never fully disappeared. The traditional woodworking, toolmaking, and precision instrument communities have maintained continuous practical use of linseed oil as a metal lubricant and preservative across generations of craftsmen who understand through direct experience that its film-forming properties produce superior long-term protection on precision metal surfaces compared to petroleum-based alternatives that evaporate or oxidize more rapidly under ambient storage conditions. Gunsmiths and precision instrument restorers consistently document boiled linseed oil as their preferred protective treatment for precision metal components requiring long-term storage, noting superior film persistence compared to petroleum-based rust preventatives. The agricultural equipment community has maintained linseed oil use for chain, cable, and exposed mechanism lubrication in outdoor conditions, where its water resistance outperforms petroleum spray lubricants under wet cycling. To apply linseed oil as a mechanical lubricant and preservative, use boiled linseed oil, available at any hardware store for $3 to $5 per quart, rather than raw linseed oil. Boiled linseed oil contains dryers that accelerate polymerization, producing a protective film more rapidly under ambient conditions. Apply a light coat to clean dry metal surfaces with a cloth or brush, working the oil into any surface texture or machined features. Allow to cure for 24 hours before returning the component to service. A Victorian maintenance engineer in 1860 applied linseed oil to the bearing surfaces of a textile mill with the confidence of someone applying a material whose performance had been confirmed across decades of industrial practice in the most demanding mechanical environment of the era. He was not using linseed oil because nothing better existed. He was using it because the accumulated engineering knowledge of his profession had identified it as producing reliable lubrication performance across the conditions his machinery encountered, and because the engineering literature of his period documented that performance in terms specific enough to guide correct application. That knowledge did not become obsolete. It became inconvenient for the manufacturers who needed a replacement cycle to generate revenue, and for the industry that grew around that replacement cycle across the following 60 years. A synthetic lubricant product manager at a petroleum company in 1965 understood that a natural agricultural oil available at any hardware store for $3 represented market share that proprietary synthetic formulations could capture if those formulations could be positioned as technically modern replacements for traditional alternatives.